All right, hello and welcome everyone. We're going to be getting started in just 2 minutes, right at the top of the hour. And so thank you if you are just joining. Make sure everybody has a few moments here to make sure they're connected to the audio and are able to see the screen share. We have not gotten started yet, so if you're just joining, just feel free to hang tight until the top of the hour. Thanks so much. Once again, if you joined us, we're going to be getting started right at the top of the hour. So hang tight and we'll be getting started momentarily. Okay, it does look like folks have been able to join, and it is now noon Eastern time. So hello and welcome everyone. Happy to have you with us today for this month's technical webinar as a part of the ongoing series hosted here by Power America. We are excited to have you all with us yet again, and we have a great presentation lined up and lots of time for discussion and Q&A as well. Before we get started, I just want to give folks a reminder that there is a Q&A module here in Zoom. So if you take a look at your Zoom toolbar at the bottom of the screen, you'll see the Q&A button. If you click that, this allows you to enter in questions in text and submit them. We will save our Q&A discussion until the end of the presentation today, but you are welcome to ask your questions at any time. So, if you have a question while the presentation is happening, feel free to enter it into the Q&A module. And then when the Q&A session begins, we'll work through the questions that have been submitted. So don't wait until the end. You can ask your questions at any time. Also, it may be helpful if you reference a particular slide number, if that is relevant to the question that you are asking as well. All right, and I think that's it in terms of logistics. So without any further ado, I'd like to introduce Dr. David Graves, who is with us from Texas Tech University. So Dr. Graves received his bachelor's, master's, and PhD in electrical engineering from Texas Tech. And while there, he conducted research with the Center for Pulsed Power and Power Electronics Lab, focusing on characterization and technology, TCAD modeling for silicon carbide, drift step recovery diodes, and semiconductor opening switch diodes. After completing his doctoral studies, David transitioned to a joint postdoctoral research associate position at the Global Laboratory for Energy Asset Management and Manufacturing and the Critical Infrastructure Security Institute at Texas Tech. In this role, he assessed cyber physical vulnerabilities and grid-oriented systems to develop mitigations that could be deployed to enhance resilience and reliability in power systems. In 2025, he joined CISI as a SCADA engineer to help to further investigate these cyber vulnerabilities in a OT environment, building on his prior work in energy systems. David also serves as an instructor in the Department of Electrical and Computer Engineering at Texas Tech. He teaches courses on semiconductor power devices and on power converter design. And so we are going to get a taste of all of that experience through this presentation today, which is going to focus on design and simulation of a high voltage silicon carbide semiconductor opening switch diode. So Dr. Graves, we are grateful to have you with us today. We look forward to your presentation, and we're going to turn it over to you for now.
All right, thank you, Emmanuel. Thank you for that introduction. Yeah, so we'll go ahead and begin the discussion on design. Oh, can you hear me?
Yes, loud and
Okay.
clear.
Okay, great, great. Yeah. So we'll go ahead and begin the discussion on design and simulations of a high voltage silicon carbide semiconductor opening switch diode. Before we begin, I do want to thank our sponsors on this research, Sandia National Laboratory, for their continued support on this initiative. So with that, we'll talk about some of the overview. So to begin, we'll talk a little bit about the different facilities I'm associated with the Pulse Power and Power Electronics Lab, the Critical Infrastructure Security Institute, and Gleam. Then we'll go over some of the research motivations and goals behind this project, a little bit of a background on these specific devices, talk about the research structure and plans, some of the preliminary simulations that were done, and then the final simulations and results. Then we'll conclude and offer some time for questions if anybody has any. So a little bit of an overview, as we heard from the introduction. I've been associated with three different groups here at Texas Tech University over the past few years. Started with the Pulse Power and Power Electronics Lab, and then transitioned to Gleam, or the Global Laboratory for Energy Asset Management and Manufacturing. And then now I'm currently with the Critical Infrastructure Security Institute. And so, as we'll see from the overviews of these facilities, they're all interconnected, and SiC really pulls them all together. So first we'll look at some of the capabilities and earlier work that we've done at the Pulse Power and Power Electronics Lab, or P3E. So one of the biggest things that we do, and that is very applicable to Power America, is a lot of reliability testing on wide bandgap and ultra wide bandgap semiconductor devices. Right, so we've done most recently a lot of work on H3TRB, or high humidity, high temperature reverse bias. We've also done a lot of work on all the other tests following the JEDEC standards, including time-dependent dielectric breakdown, high temperature gate bias, high temperature reverse bias, and so on. We also do a lot of dynamic testing, like repetitive hard cycling or hard switching, thermal cycling, and with that. And so we have various different test beds that we're able to utilize to conduct this. And alongside that, we have thermal chambers and a lot of different facilities that we can facilitate various testing capabilities. One of the other areas that we're looking to get into, and so we'd love to hear any questions of potential collaboration from anybody in the audience, is semiconductor packaging. When I attended Power America, the meeting a few months ago, one of the big emphasis was actually on semiconductor packaging for elevated altitudes. And so that's something that we are wanting to get more into. So we have a lot of different capabilities already, but would love industry partners to help facilitate all of this work that we're intending to do. So this is just some of the early initial packaging efforts that we've conducted. This one here, the silicon carbide drift step recovery diode, is one that we'll actually talk a little bit more about in detail here in a minute. And of course, at the Pulse Power and Power Electronics Lab, another big emphasis is on power electronics. So we've done numerous different power converter designs, and we continue to do that as well. So some of the examples here is some work that we did in collaboration with C5ISR as part of the Army Research Lab. And these are 10 kilowatt converters that were all interconnected to each other for mobile vehicle applications. And then stepping into the pulse power side of things that the Power Electronics Lab also works on. This again is pretty applicable to Power America, being that we're looking at the application of wide bandgap devices. With this was some solid state directed energy applications that we've looked at, where we wanted to use a Class E power amplifier using GaN HEMTs to do directed energy attacks on drones. And so now I'll transition over to some of the work that Gleam has done in the past. So Gleam is the Global Laboratory for Energy Asset Management and Manufacturing. And basically what it is it is a microgrid site. And so we can see the layout or the model of our microgrid site. And everything here has a physical counterpart as well. So we do a lot of modeling. That's what this is here. But we do have all of these physical assets actually on the ground that enable all the real world testing, right? So we have 150 kilowatt photovoltaic array. We have 130 kilowatt hour battery system. We have a 569 kVAR diesel generator. And then we have variable loads that we're able to model some of the usage, right? So we can model anything up to 500 kilowatts. or 500 kVAR. One of the things that we also recently have included into the Gleam microgrid is a NSF sponsored data center. And so we'll look a little bit more at that research here in just a moment. So a bit of the overview on some of the research. One of the biggest things that we do is building management for microgrids. So we look at various load shedding applications. This work was sponsored by the DoD and was done to look at how we can keep military bases up and operational for extended periods of time in the event that the local utility grid goes down. So with that, we developed different control algorithms to dynamically adjust the actual loads to meet the availability from our local generation. Tied more into Power America, again, is some power electronics work. So we looked at grid forming inverters, and we also are currently looking at that again. So the big thing on grid forming inverters is they're able to have an embedded computational horsepower or some artificial inertia in them to allow the system to be operational independent of the grid. And so that's great as we increase the amount of renewable penetration into our microgrids. And so for data center management, this is another thing that I saw was very big at the Power America meeting a few months ago, right? We're looking at how we can adopt the data center control algorithms to throttle data centers up and down in response to renewable energy generation in order to stabilize the grid and cut down on the non-renewable energy usage. And so this is a 200 kilowatt data center that we had just stood up that was sponsored by NSF. And so with that, we are looking to have a control algorithm that'll predict the forecast energy, tie that into our battery system that we have there, and dynamically adjust how much energy the data center is using to match that availability for renewables. And that ties directly into the other part of the research where we're looking at controlling everything else outside of the data center as well using the same control algorithms. And so we can see just another diagram of how that's set up using our 500 kilowatt generator, our solar array, our various loads, and the forecasting. And so now with the current group I'm at, the Critical Infrastructure Security Institute, being that they're an institute at Texas Tech, they really are the umbrella and they try to tie in all of the laboratories underneath them. And so with this, we're seeing a lot of coordination between the Pulse Power Electronics Lab, Gleam, and all the other facilities across campus. So with this, the biggest emphasis is national security, looking at how we can take care of all of our critical infrastructure across all the sectors. The most applicable one, I think, for Power America is the power grid, right? There's a lot of energy assets in there that use power electronics, especially as we begin to transition more into solid state devices. And so in here, we can see some of the other assets that the Critical Infrastructure Security Institute does have available. And I'll emphasize a little bit more about what we can do with potential collaboration as well and tie that back to some of the work that's done at the Pulse Power and Power Electronics Lab. So we recently acquired a Rigaku high voltage CT lab. So this is a computed tomography X-ray scanner. And so with that, we're able to look inside of devices. We can look at different things. So tying back to the national security side, one of the big emphasis is supply chain management and supply chain verification. This is an example of one of the things that we could do is if we know what the known good sample is of a device, we can look inside and detect any sort of counterparts or counterfeit samples. As you can see in the actual lead frame of the device, there's different patterns, and we could use AI models to actually scan these devices, do the image processing, and detect any of these counterfeit samples. But more towards on the power electronics side, one of the things this would be really great for is when we move into that packaging work, as I mentioned. So we could look at big high voltage modules, high current modules, look for any sort of degradation inside, maybe porosity inside of any of the solder joints, things like that. So a very good tool that we're looking to utilize. I won't spend much time on this slide. But just wanted to emphasize again from the national security standpoint, one of the things that SiC is really emphasized in is data forensics of OT systems. This does have some overlap, right? If we look at the OT systems as related to grid connected systems, um, but a little bit different than the actual power devices that we'll be talking about today. So now we'll begin actually talking about some of the research motivations for this work here, particularly on the SOS and DSRD. One of the biggest emphasis for this is they have been proven to be a viable and effective driver across many different applications, whether that be for high current electron beam generation, for ozone generation, water purification, medical X-ray generation, or even gas laser pumping. And if you look at all of the research that's been done, they've sparsely been studied over the past 40 years. And when we look at the actual concentration of where all that research is coming from, we can see this large group here. And this is based out of Russia. And so tying back to that, you can see almost all of the direct collaboration for semiconductor opening switch publications do tie back to that group in Russia. So here domestically, that has really left us kind of behind the ball. And that's one of the emphasis on why we're wanting to look more into these devices. One of the other motivations for this research is moving it into wide bandgap devices. Currently, almost all of the work is extensively on silicon-based SOS devices. And with that, they end up stacking over 100 devices in series with multiple legs of 100 in parallel in order to increase the maximum output voltage of the system. And we'll see how moving to silicon carbide actually does reduce the number of devices by an order of magnitude for the same peak voltages. Of course, by doing that, reducing the number of devices, we're able to reach far greater peak voltages. We're able to increase our power density of the systems. All of things are really great for defense applications. So as a bit of a background on how these devices actually operate, we'll first look at how they're used in a circuit. So the overall pumping for an SOS and DSRD are very similar. We'll see in the next slide how the actual physics works behind them. But the main difference between the DSRD and the SOS is mainly the time scales on which we're looking at the pulses. But if we look at our test bed here for the simplified circuit, we begin with C1 initially charged to some voltage. And then at T0, we close our switch and we begin forward pumping the device. And so as no surprise to anybody, we have a small voltage drop across our diode and we have a sinusoidal current that is dictated by our capacitance and our inductance value for forward pumping. And that gives us these characteristics here. So once all that energy is then stored back up in the capacitor, we begin oscillating back in the other direction. And to preface before the next slide, the DSRD and SOS operates somewhat similarly to a pin diode. And so we're dealing with a very large reverse recovery effect. And so with that, our device is still conductive, even while we initially reverse bias it. But what this allows us to do is really increase the current by altering our inductance. And we're able to store up a lot of energy in our inductor there. And so during this reverse pumping minus time, you can see we have a very large increase in our current through the device, which means our current in the inductor. And then we have a small voltage drop across the device. And so after some finite period of time during this R plus, or once we hit R plus, we begin to actually hold off a voltage. And so with that, we interrupt our current and we have a very large DIDT. And because of that inductor, we get a very large voltage boost to our load, right? We have the large LDIDT component plus the initial charge that is on this capacitance that now the load is seeing. And so that's what produces this voltage here shown in blue. And so this is really great for pulse power applications, right? The overall concept of pulse power is we store up energy over a long period of time and then release it all instantaneously or as instantaneously as possible. And so that's exactly what we're doing with this type of device, right? We're storing energy. First, we're charging up the device itself, and then we store energy in the inductor, and then we release it in a very small pulse to the load itself. Okay, so now we'll talk a little bit about the solid state physics behind these two devices. So the DSRD, or the drift step recovery diode, and the SOS diode, as I mentioned, operate very similarly, albeit on slightly different time scales. And so we'll see during forward pumping, as we saw on the slide before, we begin to inject charge into the base regions. And so this happens over some period of time. And we continue to inject our carriers into that base region until we end up with some plasma distribution or injected minority carrier concentration. And so for the DSRD, one of the things we'll notice here is that it is asymmetrical shape. And the reason it's asymmetrical is because of the pulse widths in which we're forward charging at. So the forward pumping times for the DSRD are typically going to be smaller, in the order of maybe tens of nanoseconds. By contrast, in the SOS, we end up with a more symmetrical shape because we're going to be pumping for up to 100 or a couple hundred nanoseconds. And so that actually leads to somewhat different physics in the actual opening. And we'll see that as we begin to start reverse biasing or reverse biasing the device and sweeping our carriers out. And so we began to sweep our carriers out in both of the devices. One of the things that we'll notice on the SOS diode is we do actually begin to form a space charge region at both the P plus P junction and at the N plus N junction. And that is before we have all of our carriers out of the device, actually. And that happens once we hit our saturation velocity for both the electron and holes. By contrast, with the DSRD, we do not form the space charge region at this moment yet, as we just continue to pull the carriers out with that reverse current. And so this continues on the SOS. We actually increase that space charge region. It begins the actual opening effect, but it is going to take slightly longer because we already have that space charge region formed, which slows down some of the current extraction. By contrast, we're continuing on the DSRD to sweep them carriers out until we hit the point where everything is swept out and we have no carriers left in the device. As soon as that happens, we're able to hold off voltage at the PN junction. And that's what makes the DSRD so fast. So a typical interruption time for a DSRD is going to be, single nanoseconds, maybe up to 10 to 20 nanoseconds on the very long side. By contrast, with the SOS device, you can typically see interruption times from 10 to 20, 30 nanoseconds. And so that's one of the biggest distinguishing factors between them, is where the actual space charge region is formed and how fast that interruption actually occurs. So the DSRD is going to be faster, but with that comes the caveat of typically lower energy. So with the DSRD, being that we have no carriers left in the device, we begin to expand that space charge region extremely fast and hold off a very high amount of voltage. By contrast, with the SOS, we begin to increase that electric field. We still have carriers in the device, and so we're going to leak some finite amount of current, slowing down our interruption time. We also eventually will hit the critical electric field, leading to some small avalanche breakdown in the device, basically curtailing the last bit of current cutoff for the SOS device. So highlighting some of the previous work that we've looked at in the literature, as I mentioned, a lot of the SOS work was on silicon. So for comparison, we're trying to look at some of the silicon carbide devices, and most of them end up being purely for DSRDs, so the much faster but lower power capability devices. We can see kind of the power levels that we're looking at, or the voltage levels that we're looking at. In most recent years, we've had a single device that goes up to 6.2 kV. In this one, they're doing 5 stacks of dies to get a total package device of 14 kV. Just a few years back, Ilion presented on a stack of 8 diodes at 1.5 kV each, giving us a total device breakdown of about 12 kV. So we can see a gradual trend towards these higher voltage devices, and that's one of the motivations behind this research. We can also see, since they are DSRDs, we are going to be looking at really fast rise times or full width half maxes, depending on what metrics the authors intended to publish. But we can see everything is in the order of single nanoseconds to even sub nanoseconds for some of these demonstrations. And so now we'll talk a little bit about the initial work that started all of this. So one of the things that we did was we were provided with a silicon carbide DSRD from Sandia National Labs. With that, the intended goal was to create a model to match the physical device characteristics. And so that began by doing some curve trace comparisons, right? So in this plot here, we're looking at some of the differences between what was provided from the manufacturer on their data sheet versus what we were ever able to achieve. So some slight discrepancies in that, likely due to some of the different packaging methods they may have used when characterizing the device at the fabrication, on the fabrication side. But in our device, we ended up with slightly different results that we ended up wanting to empirically match. One of the other things to note with this is we were given bare die devices. So we'll see an image of the actual die here in a minute. But that became somewhat of a challenge for us. We can see in some of the reverse breakdown curves, we were not able to accurately characterize it in reverse bias because the device would break down prematurely. And that was even with different various mitigation techniques, like putting the entire device inside a bath of floor inert to prevent breakdown around the device. So with that, we needed a test bed to actually characterize these devices. And so that's what was constructed here. And so with this, we can see we have the control circuitry that enables the closing and opening of switch 1 and switch 2. We have our power supply. We're using to charge C1, our DSRD that we're using in the circuit. Our load is a 50 ohm terminator. We have a Rogowski coil to our oscope to measure the current. And then we have the inductor here that we're able to sweep between. And so one of the things that is very particular about both DSRD and SOS devices is their operation is heavily dictated by the circuit they are in. And so one of the things we have after the fabrication of the device to control that is the C1 and L1 values. And so with that, we wanted to make this test bed where we're able to take these capacitor boards out and the inductors out, swap them in and out in order to sweep across various different conditions. And so with that, we have some nominal values for our capacitors. So we intended them to be 5 nanofarads, 10 nanofarads, 25, and 50 nanofarads for our sweep. And then on our inductors, we intended them to be 75, 150, 300, and 600 nanohenries. And so one of the first things that we did on the modeling efforts was to consider some of the practical design considerations of the DSRD based purely on what was provided to us. So with that, the first thing we could extract from looking at the physical device was to estimate the active area to be equal to the anode contact size. So we can see this is the device here under the microscope. We can see the anode contact here is about 1 millimeter wide, while the entire die is 2.43 millimeters wide. So with that, we ended up with an active area of 7.85 times 10 to the negative 3 centimeters squared. And then the next thing we could do is begin to estimate the minimum base width and max base doping concentrations to use in our simulations. So with this, I used the Balaga's breakdown equations for both the breakdown voltage and depletion width in order to calculate that. And so assuming an edge termination efficiency of about 80%, we end up with a parallel plane breakdown voltage of 2.125 kV. Plugging that into the equations from Balaga, we end up with a base doping concentration of about 1.6 times 10 to the 16 per centimeters cubed. And we end up with a parallel plane width of about 2.1 microns. And so based on that, we began to model the device in Silvaco Victory device. So that's our TCAD software of choice. And then over time, we ended up making some alterations to the structure based on some literature, also some feedback from field experts over the duration of the research, and on empirical testing, right? The main goal was to characterize that physical sample and make the TCAD model match it. And so the final structure that we came up with was shown here. This does deviate slightly from the suggested DSRD structure. However, as I mentioned, based on some of that literature and feedback from field experts, we believe this device, while denoted as a DSRD, should have a structure more akin to a traditional pin diode. And it is not uncommon to get the DSRD effect from a pin diode. In fact, that was how it was initially found. In Russia, they were testing some devices, some pin diodes, and actually found that the reverse recovery effects from that pin structure ended up performing slightly different, giving that very high current interruption. And that's where the optimization parts came about, was based on that structure alone. And so with that, we began to model the characteristics of the device, beginning with forward IV. With this, the two big parameters that we were able to extract in our TCAD model was the packaging and contact resistance. And so we found that to be about 50 milliohms, and then the recombination times for the device. So by altering the recombination times, we're able to adjust the knee portion of our forward IV curve. In order to get it to match relatively well to our datasheet curves, we found that using a tau n naught and a tau p naught of 50 nanoseconds was ideal. Next, we wanted to estimate the reverse breakdown characteristics and make sure that that aligned relatively well with the characteristics that were provided to us. So when we actually looked at the breakdown curve provided by the manufacturer, it was actually about 1.9 kV rather than the 1.9 kV rather than the 1.7 kV nominal value. So with this, that means our theoretical parallel plane breakdown would be about 2.375 kV. And in our simulation, you can see we're just past 2.5 at 2.55 kV. So relatively close match there, matching our physical device in theory. And so then we moved into actually doing some transient simulations in our TCAD modeling software in order to look at that characteristics of the device and optimize that structure, as I mentioned, in order to match the empirical data. So with this, there was some additional elements that were added. We added some series inductance to account for some of the packaging inductance, as well as the fly wire that we use to connect the anode of our device to the PCB. We ended up adding RS, as we found from the forward IV characterization process. And then we added CPL, which is our capacitance parallel to our load, which accounts for some of the output capacitance by the oscilloscope probe. And so with this, we started looking at the lower corner. And so as I mentioned, we had the various ranges of capacitance and inductances. And so with that, the lowest corner was our lowest inductance and lowest capacitance value, that being 5 nanofarads nominally and 150 nanohenries nominally. Measured, they came in a little closer to 5.5 nanofarads and 360 nanohenries. And when we actually simulated it in order to get the curves to match relatively well, as we can see through these characterizations, we ended up needing 6 nanofarads and 500 nanohenries. So again, within some reasonable margin of error when we're talking about relatively small inductance values and capacitance values. Looking at the peak output voltage, our peak voltage measured 216 volts, whereas our simulation measured 218 volts. So again, a very good fit there. And our rise time, again, matched relatively well at 3.6 nanoseconds measured and 3.8 nanoseconds in simulation. And those are going to be our 10 to 90 rise times. And we can see on the current side as well, it matches extremely well, giving us the same characteristics, the same approximate amount of peak forward pumping current and our reverse pumping current. Now looking at the upper corner test with our highest capacitance value and our highest inductance values. So that's 50 nanofarads, 600 nanohenries, or measured at 52.5 nanofarads and 590 nanohenries. In simulation, we ended up with 52 nanofarads and 700 nanohenries. And we can see the deviation between the measured and simulated are again roughly the same. We have about a deviation of 110, whereas in the other one, it was slightly over 110. So within that margin of error that we would expect from simulation to empirical data. Looking at the peak output voltage, we measured 201 volts, where our simulation was at 200 volts, and our measured rise time was 3.4 nanoseconds, where in simulation it was slightly longer at 4.2 nanoseconds. One of the things to mention with this when we're looking at our peak output voltages, these are not very impressive values on their own, being that we're only getting a gain of about 2x, being that we charge to 100 volts, as we are showing here. However, I just want to emphasize that the goal of this work wasn't actually hitting peak powers at this point. It was mainly about the characterization aspect, right? So it doesn't actually impact the research to only get a gain of about 2x. From these devices, you can expect anywhere from 3 to even upwards of 10x in practice if you optimize the circuit around the device itself. So now jumping into some more of the research process, this is going to be transitioning over to the SOS side of things. And so that's where all of this was built upon, right? So we took the silicon carbide DSRD, extracted some of those physical parameters from the device, and we're going to use that as the basis for the modeling efforts on our silicon carbide SOS diode. So we'll begin with the initial diode structure over the next few slides. And so one of the first things that we wanted to do was select the active area. So we went with to match the same device that was given to us by Lawrence Livermore. They provided us with a silicon SOS diode, and their larger ones had an active area of 1 centimeter squared. And so we went ahead and copied that as well. Following that, the next design parameter, again, would be the minimum base width and max doping concentration using the Balagha's equations for that, intending to get a theoretical breakdown voltage of 20 kV. We found that our base doping concentration should be about 8 times 10 to the 14 per centimeters cubed. And our parallel plane width should be about 166.5 microns wide. So using that, we came up with this initial doping profile. Following that, we did some optimization work to work on it. So again, based off of the initial DSRD work, we took the lower corner and upper corner circuits that were demonstrated earlier, and we can see them again here. The only difference now is we're going to be charging to 2 kV as we're wanting to get a higher peak voltage out of these devices, being that they're the silicon carbide SOS diodes. And the idea behind using these two upper and lower corner circuits is now we have the full range, right? We should be able to model anything inside these two corners to a fairly high degree of accuracy. So we can see, as I mentioned, these are the same circuits, albeit with different charge voltages. So with that, we looked at a lot of different parameters on the structure. So we can see how some of that is denoted here. And with that, we ended up doing a logical incremental process, where first we swept the P plus P and PN junction depths. So we can see the P plus P depth is the depth from our anode contact, basically, to that P plus P junction. And then the PN junction depth is going to be, of course, where our P material meets our N material. You can see we did a step size of 10 microns, and we had boundary conditions of 110 microns. So we swept all the way in between that. We then moved on to a P plus P and PN junction depth, where we're looking at the depths again. We refined it and did smaller steps in order to converge on a more accurate, a more ideal solution. Then we moved into the P plus P and N plus peak doping concentrations. And then we moved into the P region doping concentrations. Then we looked at the N doping gradient. So this distance from our N plus N junction all the way to where we hit our substrate. And then we looked at the breakdown voltage, which would alter our width here and the doping concentration. And so doing these optimization sweeps, we found some curves here. With that, we found that for the lower corner circuit and the upper corner circuit, we found peaks at 40 and 45 microns respectively for our P plus P junction depth. For our PN junction depth, we ended up finding peak output voltages at 10 microns and 20 microns. And so we decided to split the difference and optimize between both circuits. And with a P plus P junction depth of 42.5 microns and a PN junction depth extending that to 15 microns. Looking now at the P plus P and N plus doping concentrations, again, optimizing around that peak output voltage, as that's one of the primary metrics for these devices. We found a peak at 1E19, and we found marginal increases in the upper corner circuit once it went past 1E19. And again, we saw marginal increases in both circuits for the N plus doping concentration past 1E19. And that helps from the manufacturing standpoint, not having to hit that high solubility limit of silicon carbide, particularly for our substrate. And so we ended up picking 1E19 as our ideal doping concentrations for those regions. So with this, we moved out from the 2-parameter sweeps to single parameter sweeps. And so we can see the curves in these 1D graphs with these trend lines plotted here. And so looking at the P region doping concentration for the lower corner circuit, we found that peak at about 1E17. And with the upper corner circuit, we found peaks at 1E16. So we can see there's some benefit to going lower. But the impact once we get lower, then 1E17 begins to diminish. So it's not worth it. We found some small correlation between the in-region gradient length. So we found a peak at 20 microns. However, the trend line suggests that an abrupt junction is lower. And then same for the upper corner. We found some small correlation. We can see we're only getting a difference of 100 volts, which is relatively small when we're looking at the overall percentage increase. And then looking at the theoretical breakdown limits, we find a peak for our lower corner circuit at 17.9 kV. And with our upper corner, we end up with a peak at 10.5 kV. And so one of the reasons why we see that is because there's a crossover point. Because of how much charge we're storing in the device, that changes the operation of the circuit. As I mentioned, you really need to optimize the circuit around the device, or if you have a fixed circuit, then you want to go and optimize the device for that circuit. But based on an overall gain, we went with a theoretical breakdown voltage of 17.9 kV for the single device. So putting all of the information together from the previous slides, we have the figures shown here. And so now we'll look at some of the circuits. So the first thing we did was included some additional models into Silvaco Victory device, that being field-dependent mobility, the Class N model for low field modeling of majority and minority carriers, and alt CVT, which accounts for the doping temperature and Coulombic scattering inversion layer effects of silicon carbide. So applying all of that together and optimizing the circuit around it, we can see that we can get a 3x gain for our device. So if we do a charge voltage of 4 kV, we're getting about 12 kV out. With this, we have a current interruption of about 1.6 nanoseconds, giving us a slew rate of about 1.5 kiloamps per nanosecond. Our full width half max of our pulse delivered to the load is 2.4 nanoseconds, and we end up with a peak power of 2.9 megawatts. And then we end up with 30.8 millijoules being dissipated by the SOS diode, with only 5 millijoules being transferred to the load. But we're able to optimize that. But before we do, I wanted to show some of the extractions of the electric field and the plasma distribution in our device as we reverse bias it. So this begins at the moment of reverse pumping. And so we can see the increase in the electric field, and we begin to see the movement of the plasma. And so we end up with that distinct 2 space charge regions that are formed at the P plus P junction and at the N plus N junction. We also notice the asymmetry in magnitude that is consistent with the SOS diode. And so this overall movement of this plasma distribution, along with the generation of the electric field with the specific locations, actually do match the fundamental aspects of the SOS that has been theorized. And so now we're able to confirm that that does happen in silicon carbide. So now if we were wanting to look at the breakdown voltage of the device, we can see too, being that we have the space charge region actually being formed in the high doping region rather than the base, we're able to actually have a higher breakdown voltage. And so during the pulse, even though in DC we're only able to hit 17 kV, if we charge the device with 10 kV, we can get a 22 kV pulse out going beyond the DC breakdown. Now looking quickly at the higher conversion efficiencies, if we optimize the circuit again, we can actually do basically the same thing as before, but now we're able to get a conversion efficiency of 57.5%. So we're delivering most of the energy to the load rather than dissipating it into the diode. As we can see here, we're only consuming 9.3 millijoules of the initial 24 millijoules that was given on the capacitance. So the next thing we want to do is stack these devices up. So if we stack 5 of them up in series, we have an 85 kV breakdown in DC. And if we charge with 50 kV, optimize some of the L's and C values here, we can get a system that produces a 95 kV pulse with a full width half max of 1.3 nanoseconds. And that stack is able to interrupt 5.8 kiloamps in just over 1 nanosecond. And so this stack allows us to deliver 180 megawatts to the load. Just zooming in to see the peaks. And so how does that compare? As I mentioned, a lot of the devices that have previously been published on are silicon-based, and we can see various test beds that were published by some Russian authors. So we can see what the peak output voltages range, and you can see we're on track with some of their lower voltage ones. We are hitting higher peak currents than them. But here's the big thing. If we look at the peak power, we're right on par with some of their bigger systems, right in between. But with that, they're using between 160 devices in series with 2 parallel sets, meaning 320 devices, upwards of 600 devices. Whereas by contrast, we only need to use 5 of silicon carbide devices. And so if we extrapolate that for max power generation per device, you can see significantly higher returns using the silicon carbide SOS device. We're getting 36 megawatts per device, where best case, they're hitting upwards of 1 megawatt per device. And so one of the things that we continue to iterate on with this is different structures based on increased carrier lifetime. If we're not directly bound by the carrier lifetime from our characterized device, we're able to increase that to higher amounts, right? As we mentioned earlier, we were using 50 nanoseconds. We can increase that to 500 nanoseconds, which is still reasonable for silicon carbide. But that basically will increase the carrier lifetime, allowing us to have a higher injected carrier concentration. And this increases the reverse recovery time, meaning we can store more energy in our inductor, leading to higher energy systems. And so by adjusting our tau n naught and tau p naught to 500 nanoseconds, and then optimizing the device structure slightly, we can see some different results here. So in this figure, we're charging to 3 kV. This is the circuit used, very similar structure, just different values. So now we're using 15 nanofarads. We're using 500 nanohenries in forward pumping and 150 nanohenries in reverse pumping. And we're able to get a voltage gain of 3x, meaning the single device gives us a 9 kV pulse. The big difference, though, is now we have much wider full width half max, much higher energy delivered to the load. So we have a full width half max in this system of 14 nanoseconds. By contrast, we were looking at single nanoseconds with the lower lifetime. Peak power, fairly similar at 1.7 megawatts. And then when we're looking at stacking these devices again, we can do some more optimization. And we can see the full width half max of this system is 17.7 nanoseconds. And we're breaking 14 kiloamps in 10.5 nanoseconds. Again, that's the 10 to 90 time. And we're getting that peak voltage of 121 kV with only initial charge of 35 kV. So we get a system gain of about 3.x, and we actually deliver 300 megawatts to the load. One of the caveats to note on this simulation is we are using multiple strings in parallel, not just the 5 devices in series. So we wanted to increase the overall active area, and so we end up with uh, 10 strings in parallel of 5 devices. So it was 50 devices. By contrast, in the earlier simulations, we were only using 5 devices. So to conclude, one of the biggest takeaways from this was the SOS effect was demonstrated in simulation for the first time in silicon carbide. With this, we saw the distinct two space charge regions that were formed inside the P and N regions, with their expansion coinciding with the movement of the plasma distribution during that reverse pumping phase. Both of these aspects mirror the historical analysis of the SOX effect in silicon carbide, or in silicon, I should say. With that, we did demonstrate a high voltage SOS diode, which had a DC breakdown voltage of 17 kV, and we could generate 20 kV pulses with that. With that, a 2.5 kiloamp current interruption time of 1.6 nanoseconds, which demonstrates the very fast cutoff effect from our SOS diode. We're able to get a voltage gain of about 3x on these devices, with our pulse width being 2.4 nanoseconds across our 50 ohm load. Again, when we put 5 devices in series, we get a DC breakdown voltage over 80 kV, and we can use that to generate a 95 kV pulse across a 50 ohm load. Throughout some of the simulations, we did show a peak conversion efficiency of 56%, which we believe can be further increased. One of the other things demonstrated was the benefit of increasing carrier lifetime and then re-optimizing the device structure. We're able to get a higher system gain, and alongside that, we're able to get much higher energy systems. So again, with the 10 devices in parallel, or 10 strings of 5 devices in parallel, we ended up with a 120 kV system. And so with that, we're right up on time, and I will stop and take any questions.
Okay, fantastic. Awesome. Thank you, Dr. Graves. We appreciate the thorough presentation and all of the improvements and the advancements that you've been able to summarize here for us, and the efforts described. We do have a few questions here, so we'll go to the Q&A module. So the first one, this was when you were describing the silicon carbide DSRD device on slide 21. It's just a clarifying question about the voltage rating of the device.
Yeah, so nominally, the manufacturer told us it was 17 kV, or sorry, not 17 kV, 1.7 kV. The issue was when we tested it in-house, we were not actually able to get up to 1.7 kV. We had premature random breakdowns. In the modeling efforts, we ended up taking their word for it, but we were not able to actually reproduce those results that were provided.
Got it. Got it. Yeah, that's significant. Appreciate that.
Mm-hmm.
Okay, we had another question here. What kind of switch are you going to use for the initial voltage pulse or spark gap?
Yeah, so let me pull up the test bed. So I don't have the part number, but these were silicon carbide MOSFETs. So that's what we were using. The biggest thing is being that we're just closing and the overall forward pumping times are fairly long in the order of 100, 200, even upwards of 500 nanoseconds. The rise time of the MOSFET isn't super critical. And it stays closed throughout the duration of the pulse. And so, faster is better, but it's not something that we actively have to worry significantly about. And so that's one of the biggest benefits, right? The driving nature of these devices are very simple.
Got it. Got it. Okay, appreciate that. And just a reminder, folks, if you do have more questions, please feel free to enter them in the Q&A module. We do have another question here. How do you handle the transient thermal pulse in the device?
Yes, that's a great question. So one of the counterparts that I was not working on, but one of my colleagues was working on, was they did do repetitive pulse modeling, and they actually did some repetitive pulse testing on the silicon SOS diodes that were provided to us from Lawrence Livermore. And so with that, we found there are limited rep rates. I believe he was able to get up to about 5 kilohertz um, rep rates for these devices, so fairly low. Historically, when you look at some of these devices or some of these test beds, I should say, coming from Russia, uh, they just actively cool them in a massive vat of transformer oil. So they'll put the whole stack, the whole stack may be a foot long, even longer, and they just submerge the entire thing in transformer oil. And so that is one way we would look at that. All of this work has been single pulse. But once we do move into the repetitive pulsing, we'll have to definitely consider that.
Okay, interesting. All right, thank you. There was a question about the recording and the slides. I do believe this webinar is being recorded, and I believe the intention is to make the slides available. Dr. Graves, if you are comfortable with that, of course.
Yeah, that should not be an issue.
Great. And we'll follow up with you to make sure we have an appropriate version for distribution.
Okay.
Awesome. Two more questions here. We have a question on the temperature effects on performance, especially in high power applications. Have temperature effects been considered and or measured?
They have been somewhat considered. It was a bit outside of the scope of this work. Again, once we get into more of the repetitive pulsing, increasing that rep rate, it will be something that we actively investigate. But up to this point, we have not personally done any work on it.
Got it. Appreciate that. And then another question here is what is the target PRF?
The target PRF, I guess it'll tie back to again the thermal analysis that we'll end up having to do. Of course, higher is better. One of the biggest things to emphasize and put out there for anybody in the audience is we would love to actually fabricate these devices, right? We would love to work with any of the fabs here and actually make these devices so we could do some of these testing situations, look at the maximum pulse frequency. We could do it in simulation, but again, simulation only gets you so far, and it'd be great to partner with anybody to actually fabricate these devices.
Actually leads to a question of mine. I was curious about if any significant fabrication challenges that you may be aware of and sort of going from the design and the simulation into a manufacturable device.
Yeah, there definitely will be when we look at this. So from some of the initial conversations I've had on some of the fabrication side of things, the very large doping depths won't necessarily, they're not necessarily a challenge. It just becomes much more cost inhibitive. And so it takes, I guess, really long to grow the device, actually dope it. And that's one of the limiting characteristics of the SOS is just how long and expensive that growth process would be.
Yeah. And I guess a related question would be if you're aware, I'm curious about commercial silicon carbide processing capabilities and how they align with the requirements for making these types of devices.
I'm not super knowledgeable on that. I would love to work with anybody directly. Some of the limited conversations I have had, um, as we continue to advance and get higher energy implanters, that should reduce the overall cost of this device. Um, but I wouldn't be able to speak comfortably on all of the challenges.
Okay. Yep, understand. Hopefully that's connections we can help facilitate here in the
Yeah,
community.
absolutely.
Yeah.
Willing to take any sort of help or feedback from anybody.
Awesome. So if you're listening now and, and you recognize that you could be helpful in this regard, please feel free to reach out and we'd love to get you connected. We did have one more question here, and this was just on the length of the pulse and if longer pulses are of interest.
It can be. It depends on the actual application. Yeah, it just depends on the intended application. If you're wanting to do, high power microwave generation, it just, yeah, unfortunately, it just depends on that. Um, Although smaller pulses are of interest, so having really small pulse widths like 1.3 nanoseconds um, is of interest in the HPM world.
Got it. So I guess one more question I could ask. We still have 2 minutes. I'll try to squeeze in maybe one more here.
Yeah.
So in that regard, I am curious. I see as the you're improving performance over time, right? And you're seeing these benefits in device increased device capabilities. And I am wondering if there are certain applications that you're pushing towards, at this time, and if there are certain like entry requirements, say whether that's interrupt time or conversion efficiency. Is there any particular targets that you're pushing towards, maybe for entry into a particular application area to displace current
Yeah,
silicon devices?
that's a great question. That's something we definitely are considering as we continue to look for funding sources. Being that this would be the driver, we would like to, I guess, tailor it to whatever the funding sources have. So as far as picking a specific target in mind right now, we don't have one. Um, but there is a lot of interest out there for very small, very fast rise time pulses, of course, and I think that's really where this would shine. So the benefit with that is, if we were able to go and come in with the exact metrics in mind, we could design the specific DSRD to generate those specific conditions as well. So that's one of the benefits behind it, benefits and drawbacks, right? You can't just pick any DSRD or SOS diode and expect it to generate the same results that you're wanting. It kind of has to be tailored for the application.
Absolutely. Okay, we got a couple last second questions here. One is, can you share the inductor design? So perhaps maybe that's something folks can reach out if they're interested in knowing more.
Yeah, I'll just real quickly show that. It's very simple, just an air core inductor. We just wrapped it. And if you're talking about the switching inductors that we're using in the simulation, traditionally they're done using magnetic switches to change that inductance. In SPICE, it's very easy to just change the value. But in the real world, I would be using magnetic switches. But
Okay.
yes, in our physical design, it was just an air core.
Yeah. Okay. And then last question here, and I guess this is considering this high current interrupt capability, folks are interested in knowing whether or not this has applicability for DC circuit breakers.
Uh, huh. I have not really considered it. It likely wouldn't just because of the way you have to do it, right? The only way to generate these interruptions, these high interruptions, is to first forward bias the device and then reverse bias it. If we go back to a pin diode, we're basically designing a bad pin diode to take advantage of the reverse recovery effects. So yeah, it just has very limited control aspects is the problem there.
Good to know. Good to know. All right, appreciate that. And we are at time. I don't want to hold anyone any longer, but I do want to say thank you, Dr. Graves, again for taking the time to provide us with these insights into this fascinating area of technology development, and for the Q&A as well. And thanks for everyone who volunteered a question and participated in the discussion. Hope everybody learned something useful. And please feel free to connect. Feel free to reach out, whether that's through LinkedIn, through the Power America Network, or otherwise. There's definitely more collaborative, able to push and to do further testing and qualification. So again, thank you, Dr. Graves. Thanks everyone for participating, and happy to have you with us today.
Yeah, thank you. Thank you for having me, and thank you everybody for attending. Really enjoyed it.
Happy to hear. All right, take care, everyone. We'll see you again next month, and look for the emails and reminders about our next webinar in the series.